Hello, I'm Professor Tolga Yarman. Over here I'm going to redo the presentation I made last month in the prestigious conference held in honor of dear friend Professor Peter Rowlands in Crete, Greece. It is the Quantal Theory of Gravity. So this is a new gravitational theory which is in no way a repair of the general theory of relativity. It is in full symbiosis with quantum mechanics, and it's applicable to all bound fields. It can be named as same outlook for both the cosmos and the atom. Now, over here I'm going to elaborate on the article Quantal Theory of Gravity, Essential Points and Applications, which we published about a year and a half ago in Annals of Physics in May 2023. Now, the way we see today's main problem is this. Actually, we cannot look at the cosmos and the atom with the same mathematical tools. In different terms, we are unable to apply the concepts we use to describe the atom to cosmological scales, and we cannot apply the concept we use to describe the macro world to the atomistic domain. So this is kind of a dichotomy we all face, actually. One of the main problems is the understanding of energy. Now, energy is a very important concept. It is kind of left undefinable in the general theory of relativity, since the concept of force is left undefined in the general theory of relativity. So force is exerted and energy is produced. So this is as simple as this. So energy is conserved means that a source must pay for its bill. So the first differential equation we write over here is dE equals to F times dr. So meaning that if the force of concern is displaced as much as dr, then the energy d is produced. The requirement this imposes within the framework of the energy conservation is that dE must be equal to dm times c squared. It is the special theory of relativity, meaning that a source must pay for the energy produced, created. Thus, combining the first two equations, we land at F times dr is equal to dm c squared. So very unfortunately, this main equation seems to have been forgotten in both the cosmological world, also in the atomistic world as well. So we applied this fundamental relationship to both the macro world, also to the atomistic world. The conclusion is that the mass, or the energy content of a test object bound to a force field, is decreased as much as the static binding energy coming into play. So one important pillar of our theory, of our approach, is UMA, the Universal Matter Architecture. It is that the period of time, size, mass, and energy to be associated with the internal dynamics of any quantum mechanical entity should, while already at rest and far away from any fields, be interrelated in a unique way insofar as satisfying the requirements of the special theory of relativity, where the given entity brought to a uniform translational motion, or those of quantal theory of gravity that I'm going to present now, if the entity gets embedded in gravity, or as a matter of fact, in any field the entity can interact with. Now, the UMA basic theorem, which I had to spend a long time to prove, really, was published first to the international scientific community in Foundation of Physics Letters in 2006. So we consider a quantum mechanical object composed of capital K particles with the rest masses m sub k0, k extending from 1 to capital K, and we assume that all of these masses are multiplied by the arbitrary number psi. So if we do that, then the following rescaling end results occur, mathematically I am speaking. So if m sub k is 0, k extending from k to capital K, is transformed into psi times m sub k is 0 K extending from 1 to capital K, then the eigenvalue E sub 0 of the initial quantum mechanical description is transformed into psi E sub 0. Thus, the period of time associated with the internal dynamics of the object of concern is transformed into T sub 0 divided by psi, and the size of the space the entity of concern is structured in is transformed, L sub 0 is transformed to L sub 0 divided by psi. So again, E sub 0 is the total energy of the object. Mathematically speaking, this is the eigenvalue of the stationary quantum mechanical object describing the entity of concern. T sub 0 is the unit period of time of its internal clock motion, and L sub 0 is the characteristic length of the space size the given motion takes place in, whereby all of the above quantities are ascribed to what we can refer to as the said object's internal dynamics. Thus, the gravitational redshift occurs owing to quantum mechanics in our approach, and as we are going to see, the same occurrence takes place in the atomistic world as well. Let me explain this just a little bit. So, the gravitational redshift means that the energy emitted by an object bound to a gravitational object, such as the sun, such as a star, is redshifted, meaning it's weakened. So according to this theorem, because the object is bound to the gravitational field, its rest mass decreases as much as the static binding energy coming into play. And now, if we visualize the quantum mechanical description which mathematically frames the object of concern, then the eigenvalue of it, because the mass is decreased already as much as the static binding energy, then the total energy of it, the eigenvalue of the description, will be decreased as much, meaning that the period of time will be stretched as much. So, which is the general theory of relativity's prediction, but only owing to the curvature of space. So we don't have any curvature of space which would be similar to what general theory of relativity brings in, but we have over here totally quantum mechanical phenomenon, which is as well valid for the atomistic world, just the way I'm going to present pretty soon. Now, this idea occurred to me long time ago. So if the mass decreases due to binding in the force field, as I described in the introductory section of this presentation, then any electron bound to the nucleus, atomic nucleus, should undergo a mass decrease as well. Of course, we cannot measure whether the mass decrease of the electron occurs or not, because the electron is assumed to be a point-like particle, and we have no way to measure how its internal dynamics will be affected when it's bound to an atomic nucleus. However, there is a very practical way of checking what I just explained with regards to UMA and its application to the gravitational redshift. We just replace the electron with a muon. Now, muon is an elementary particle, as we all know. It is about 200 times heavier than the electron. Now, if we replace in a hydrogen-like atom the electron with a muon, and the muon will be bound to the atomic nucleus, which is the proton, or in a hydrogen-like atom, Z can be higher than 1, and we indeed have in this figure Z scaling from going from 0 to more than 80, even 90. Okay, then the bound muon, so rest mass should decrease as much as the static binding energy coming into play. Then this rest mass should bring internal time period stretching, which indeed can be measured, because the muon has a half-life which is about 10 to minus 6 seconds. So if the muon is bound to the nucleus, any hydrogen-like nucleus, just to make things easier, of course, we consider a hydrogen-like nucleus. So the muon's decay half-life must get stretched. So this was the idea which occurred to me some 30 years ago, and I also conceived that the bound muon should exhibit a decay rate retardation, and I have developed the entire picture without knowing anything about data, which I got to know around 2000, perhaps a little earlier, and I've surprisingly and very happily saw that my prediction occurred to overlap exactly, almost, I would say, with the measured data. So in this figure, what we observe is this. We have in the ordinate the bound muon decay rate retardation. So it is calibrated to 1, meaning that the unbound muon doesn't have any decay rate retardation. But on the x-axis, we have z, the number of protons. So increasing the number of protons, we see that you just take a look at the triangles, which is our theory's predictions. So our prediction fits exactly the measured data. Over this curve, which exactly fits our prediction, we have the usual classical electrodynamical predictions made earlier by Hoof. The references are given over there, and they are in no way getting close to what we did. So the classical electrodynamics today is somewhat incapable, as much as we can see, to make this prediction. So this is a gravitational redshift, but occurring in the body of the atomistic world. So if a muon 200 times heavier than an electron is bound to an atomic nucleus, and it's a question of a hydrogen like atomic nucleus over here, so its decay rate is retarded. So the gravitational redshift and the bound muon decay rate retardation are the same phenomena. Now, UMA, of course, requires quite a high knowledge, I would say, in quantum chemistry. It's beautiful that our gravitational theory is in perfect harmony with quantum mechanics and quantum chemistry as much, as well as quantum chromodynamics, I would say. So it is applicable to all scales. So the UMA theorem I just stated brings in an internal relation between the parameters I had enumerated, which were the total energy, the clock mass, the period of time of the internal clock dynamics, and the size the internal dynamics of concern is structured in. So if we now, I'm unable to go into the details of this combination. So you can combine the parameters of concern 2 by 2, then involving electric charges and I would say quantum numbers, also the Planck constant, or you can combine them 3 by 3. In this figure, for instance, which sketched the systematization of alkali diatomic molecules. So you have the period of time in the ordinate, and you have m sub 0 to the power of 1 over 2, which is the reduced mass of the atoms making up the diatomic molecule of concern. We may insert the mass of the electrons over there, which is a constant, again to the power of 1 over 2, and times the internuclear distance of the alkali molecules of concern. The factor we have at the left-hand side points to the quantum numbers along with quantum defects, describing the somewhat the levels of the diatomic molecules as referred to the hydrogen molecule, where the quantum numbers of concern are assumed to be 1 and 1. So we see that over here, according to this particle combination, the hydrogen molecule, the lithium molecule, lithium-sodium molecule, the sodium molecule, sodium-potassium molecule, potassium molecule, potassium-rubidium molecule, rubidium molecule, the rubidium-cesium molecule, and cesium molecule are all aligned already in empty space and far away from all fields in just a unique way, in accordance to the universal matter architecture I have just presented. So we can as well combine the parameters of concern for taking into account 4 of them, which also we have done, but which I'm going to show pretty soon indeed. So this figure already is a quite fascinating proof of the UMA theorem I have proven and I have just stated, and it is applied to the body of the entire diatomic molecules. Also polyatomic molecules, I would say. Okay. Here Now we go to the nuclear domain. We have made a lot of publications on this. So again, we have over here the all four parameters considered together. So we consider the decay half-lives in the ordinate of this figure of all of the nuclei disintegrating, throwing away an alpha particle. We have extracted this figure from our publication made in European Physical Journal A in 2016. This is just one of them. There are very many of them. They all behave so beautifully. So in the abscissa, we have the square root of the alpha particle divided by the total energy of the alpha tunneling out times the size of the parent nucleus. So this then somewhat embodies the three of the parameters I had mentioned in Uma theorem, and the fourth parameter is the period of time of concern, which is decay half-life of the nucleus of concern via emitting an alpha particle. So as we see over here, we have we consider, of course, nuclei bearing alike shell structures, so that we can have a straight line. Otherwise, the Uma theorem is always all the way rigorous. But in order to have a constant proportionality between the period of time or the decay half-life and the other parameters combination, we must consider nuclei possessing alike shell configurations. As you see, this figure embodies osmium as well as radium and other nuclei, which you can see from a closer distance. And you can, of course, check our article published in European Physical Journal A. We have got two articles over there for even nuclei, for even and odd nuclei, and we have a third article which encompasses all other nuclei belonging to the category of odd and odd even nuclei, all disintegrating, emitting an alpha particle. So this is again somewhat the beauty of UMA. UMA is valid at every scale. It's valid at the skies, bringing in the gravitational redshift. It's valid in the atomistic world, bringing the bound muon decay rate retardation. It is valid in the nuclear domain, which brings in this beautiful systematization of alpha decaying nuclei. Now, something which occupied our mind for a long time was the beta decay systematization. We thought of it for years, I would say, but over here we don't see anything else than what I explained in the previous figure, also with regards to the atomistic world. So we have again the decay half-life for nuclei emitting a positron to release energy. In the abscissa we have that. Yeah, in the ordinate we have the predicted half-life in a log-log scale. I mean, the predicted half-life should be proportional to the square root of the mass of the positron divided by the initial energy of the positron at the moment this positron is emitted. So it requires some calculations. That times the size of the positron. So this work of ours was recently published in the International Journal of Modern Physics, E. Now, again, in order to secure a proportionally constant between the period of time and the combination of the other parameters, we had to consider the beta positive decaying nuclei, all possessing the same structure at the outer shell. So you see that we could obtain different groups. These are all indicated in the mentioned article, and this beautifully again checks out the universal matter architecture, even the beta decay of the nuclei, and we have gone through all of the beta decaying nuclei in order to be able to reproduce this figure. They do obey to the universal matter architecture. So the lines you see are parallel to the bisector of the coordinate system. This is a log-log coordinate system, and on the lines, you see different lines, we have different outer but similar shell structures of the nuclei of concern. We do the same exercise for the negatron decay nuclei. We are going to, I hope, publish it soon. We already have a fascinating outcome, which I couldn't report in this presentation. Okay, so follow up anyway, please. Now, the world of diatomic molecules is fascinating from this angle, and the UMA approach allowed us to predict that the dissociation energy of the molecule of concern times its internuclear distance must somehow decay with respect to the product of the mass numbers of the atoms, and then afterwards should increase. That prediction was made by our team by 2017, and then we obtained this beautiful figure and many others. The article is published in Molecular Physics, and we are thankful to our editors because it was a very pretentious article. It was published in 2021, and you see all of the diatomic molecules over here again bearing alike electronic configurations. So as you see, for instance, which fascinates me really, which fascinates all of us really, is that on the ordinate you see P is the dissociation of the hydrogen energy times the Bohr atomic radius. You see, take for instance the Wolfram. The Wolfram is tungsten. It is the green curve up there. You see the green curve. It decreases the dissociation energy. It decreases first, and then it delineates a minimum, and then it increases. This is kind of exciting. You know, we are talking about, of course, diatomic molecules bearing the same electronic configurations. So take for instance the plot of alkali molecules. The alkali molecules, you know, they start decreasing from PE data as we go from you know, the hydrogen atom, then to the lithium molecule, then to sodium molecule, and then to all other alkali molecules. And then, you know, that over there you see the bottom line, and we are kind of sure that it would grow up afterwards with respect to A1 times A2, which is the product of the atomic masses of the atoms making up the molecules. What is interesting is that you know, according to Gauss' law, if the atoms of a diatomic molecule were at rest, then there should not be any force in between the atoms. But obviously the charges within the atoms making up the diatomic molecules, or of the atoms themselves, the charges are not at rest at all. So they somewhat produce an attractive force making up the diatomic molecule. We all know that as well. So, but what is interesting is that we start at 14. You know, 14 is the dissociation energy times the internuclear distance for the hydrogen atom over there. It is presented, or it is represented by 14, and then, you know, we go from there for the tungsten-like molecules. You know, it decreases indeed, and then at around 35,000 as the product of A times A, you know, the attraction force is incredibly as strong as the proton-electron force. This was what we wanted to display, and we succeeded indeed to obtain this beautiful outcome. I'm not going to speculate anymore, but we have written everything in the paper. Look at it, please, if you can. And this may bring very enthusiastic insight about the the fact that the gravitational force may be somewhat the appearance of electric forces at a distance of, so to say, neutral bodies. But bodies with electric charges not at rest rigorously do leak electric field, and they do attract each other. So this was the main point, again based on our UMA. Now, what is interesting furthermore is that, unlike what we all think, quantum mechanics is valid not only within the atomistic world, but in the macroscopic world as well. We all neglect that. So the work we have presented removes any artificial boundaries between the micro world and the macro world. So we have thought a lot to that quest indeed, and according to UMA, even a gas system embedded in a volume, say a cubic volume, which we can represent by L to the power of 3, the size of the cube being L, then should be structured in accordance with UMA. This is very exciting. How come that the quantum mechanics can reign at that scale? So, as we all know, the thermodynamic relationships, almost all of them involve either Boltzmann constant and temperature. Only one of them, as we all remember, does not involve any Boltzmann constant in temperature. It is the relationship representing the adiabatic transformation. As we know, P1 V1 is equal to P2 V2 to the power of P1 V1 to the power of 5 divided by 3 is equal to P2 V2 to the power of 5 divided by 3 is equal to P3 V3 to the power of 5 divided by 3 for adiabatic transformations, and is equal to a constant. But none of us wondered about what that constant of concern would be. Now, UMA tells us that a gas embodied in a given volume, it has got, of course, all of the parameters which we cited when I stated the UMA theorem. So they must be structured in a given way. So in the gas domain I just described, that relationship with containing no temperature is P times, meaning the pressure times the volume the gas is encompassed in, is equal to a constant. Now, it's not difficult to calculate this constant in a three-dimensional world. This constant turns out to be 2 divided by 3 times the square of the Planck constant times the quantum numbers in 3 dimensions defining the state of the molecule of concern, divided by 8 times the mass of the molecule of concern, times L square. I mean, the first term at the right hand side represents the energy indeed, times the volume of concern to the power of 2 divided by 3, which comes to the expression below, which is 8 squared times the summation of the square of the quantum numbers in 3 dimensions divided by 12 times the mass of the molecule of concern. We made a lot of publications on that too. This is published in Results in Physics in 2018, and what is fascinating, this allows us to quantize the second law of thermodynamics. We find that very exciting indeed, and we have transformed the Boltzmann law as well. Let's see the next slide. So now, with all that, with this all complete world view, I would say, we come to our gravitational theory. Now, ironically enough, we go back to the Newtonian force, which we demonstrate to be a requirement of the special theory of relativity. So we don't borrow really Newton's law of gravitation from Newton directly. It is written, of course, there as a first equation. But our rest mass must get changed, as I explained in the introductory part of this presentation, in relation with the binding energy of the bound particle to the host object. So we have indeed the Newton force, but as I say, we could demonstrate that the R-square dependency of Newton force is a requirement imposed by special theory of relativity, really, you should go to my article, first articles published in 2004 and 2006 in Annals de la Fondation Louis de Broglie, also in Foundation of Physics Letters. So I'm avoiding the details really, but we have a perfect frame of the Newton force law, gravitational force law over there. The capital M is the mass of the host object. M over R is the rest mass as observed by the distant observer of the object bound to the host at a distance R from its center. So R is the distance measured from the center of the host body to the test object. So then, I write as a second equation the equation I had presented as the third equation in the introductory part of this presentation. It is that the force displaced as much as dr if we carry out the test object. So let me remind you that everything over here is static. So the masses are static. Otherwise, Newton's law is not valid. So we only consider static masses. So if we move the rest mass bound to the host body at R from R as much as dr, so we have to supply a certain amount of energy. This energy, according to Newton, is stored in the environment as a potential energy. But according to the present theory, it is stored inside of the rest mass of concern as an extra energy. So this is a simple equation which I have written for the first time in my paper published in Foundation of Physics Letters in 2006. I have written kind of a different equation, which is also very elegant, I would say, in my paper published in Annals of Physics in 2004. So this simple equation furnishes right away the rest mass, or the same rest energy, if we multiply both sides by the square of the velocity of light. So the last equation in this page displays the rest mass of the test object at a distance r from the host object center in terms of the gravitational constant as measured by Cavendish in the laboratory, times the host body's mass divided by r times c squared. This argument, as we all know, is called alpha generally. Okay. Now, what is furthermore fascinating, I would say, I was able to write the equation you see over here as a second line as a straight energy conservation equation. It is very simple. The idea is very simple. It says that if we descend somewhat the test object from infinity to the distance r quasi-statically, its rest mass will get decreased as much as exponential minus alpha. So we have now the host body and the test object, and now the test object's rest mass at this location, as is referred to the distance observer, is decreased as much as exponential minus alpha, as I just stated, at the distance r. Now, if we bring this decreased rest mass to its motion in a stationary orbit around the host mass, then I would increase its total energy by the Lorentz factor. I'm sorry, I just see that we missed at the final part of this equation m sub 0 c squared, but it's kind of a trivial error. Anyway, in a closed system, the whole thing must stay constant. It is, of course, surprising and remarkable that we have arrived to this equation in only one line. This is how I have written it really some 25 years ago. It looks very much like Einstein's general relativistic equation, which is at the last line of this page, which says that the rest energy at a distance r from the host object of the particle is m sub 0 squared, which is the total rest energy of the test object at infinity, times the square root of 1 minus 2 alpha. The rest energy is decreased by square root of 1 minus 2 alpha, and it's increased by the Lorentz factor. But the decrease of the rest energy, according to Einstein, is due to the curvature. Whereas, according to our approach, the rest energy decrease is due to UMA and to the energy conservation law. So the energy conservation law makes us write the second equation on this page in just in just a second. Whereas, in order to be able to come to the last equation of the general theory of relativity, we have to set up the Lagrangian, we have to minimize the action, we have to write out of the metric equation in differential form, and then make painful integration and so forth. But let me just warn you that our energy and our mass do vary in the same direction as referred to the outside observers. Whereas in the general theory of relativity, very unfortunately, because Einstein violated his beautiful equation about mass and energy equivalence as to delta is equal to delta m times c squared. So unfortunately, in the general theory of relativity, as I say, the energy, the rest energy, and the rest mass do vary in opposite directions. So we have over here a clear violation of the law of energy conservation anyhow. It is written everywhere that the general theory of relativity deliberately breaks the law of energy conservation. Over there, of course, we have a constant energy, or an expression, I would say, which remains constant in a given orbit in units of energy. But this is different. We never broke the law of energy conservation. Quite to the contrary, we have written everything based on the law of energy conservation. So the above equation, the second equation, as you see, is a YARK equation, as we call it, Yarman-Arık-Kholmetskii energy conservation equation. As a matter of fact, originally written by myself. So this equation is written based on state law of energy conservation. So we don't have any policy with regards to the variation of mass and energy in different directions at all. So they do vary in our theory along the same direction in gravity or anywhere else in the atomistic world as well. Just we have dealt with regards to the bound muon decay rate retardation a few moments ago. Okay. Now, once we wrote the energy conservation equation as a mathematical tool, quite differently from the classical tools used. So as I said, we didn't use any Lagrangian, no action principle, no minimization of action, which are very respectable, of course, but we don't discuss this at this moment. We don't have any metric over here. We have size and period of time change, of course, as induced by the UMA, universal method architecture I have just presented, but without using all these classical tools, just via differentiating our energy conservation equation I just have shown to you, and I have written some 25 years ago, perhaps a little earlier than that even. So we obtain our equation of motion. So this is our equation of motion, which have to be elaborated according to UMA, just the way I will explain to you briefly. And this equation of motion can be brought to a very special form as the second equation, and it is also very enthusiastic to see it the way it is, because it says that the rest mass variation through the motion, such as, for instance, the Earth getting closer to the sun, its motion speeds up. Okay, so its rest mass should decrease and should get transformed into the extra kinetic energy that it will acquire. Okay, so it says that the rest mass variation times a constant c divided by v, which we have worked out in different papers, times c times the inverse of the Rowlands coefficient is equal to the momentum change. Because m gamma, as I say, this is the constant energy if I multiply it by c squared. If you take c, the velocity of light unity, m sub gamma is the total energy I just wrote in the previous page. So this is our momentum conservation equation. It is the rest mass dynamics, as my son, Professor Ozan Yarman, called it, so that there is a dynamics meaning motion depending on, governed by a force, and the force over here is the gravitational force. And throughout the motion, if the orbit is not circular, if the orbit is nearly elliptic, then it is the rest mass dynamics, meaning that the rest mass increase, which yields a decrease of the velocity of the planet of concern, for instance, revolving around the sun, or the rest mass decrease, which then increases the velocity of the planet getting closer to the sun. So this rest mass dynamics, which governs the motion. Now, this is even more spectacular, I would say, because we have at the left-hand side of this equation a term multiplying dm, absolute value of the change of the velocity, which is a velocity, obviously because it's a question of a momentum. Momentum is a mass times velocity. So this velocity in ordinary cases is greater than the speed of light. Since it's greater than the speed of light, it cannot carry any energy. But by the same token, it brings up the quest that I'm going to come up with pretty soon again. It brings up the quest that the interaction between two bodies can be achieved either by exchange of energy, then this cannot be faster than the speed of light, or the speed of interaction between two bodies can occur with a speed greater than the speed of light, then excluding any exchange of energy. And this is what happens in the gravitational world. Even in the atomistic world, the interaction between the atomic nucleus and the electron, the speed of it is greater than the speed of light, and it excludes any exchange of energy. So the physicists love to call it a virtual, they exchange particles as virtual photons, but as an engineering professor, I hate talking about virtuals or phantasmagorics or anything not real or realistic. So I respect them very much, of course, but this equation just tells us that there is no exchange particle at all between the sun and the planets. So they are locked quantum mechanically, and the speed of interaction between these bodies are, ordinarily speaking, greater than the speed of light. We find this fascinating again. So far, I made use of the law of energy conservation. I have introduced UMA, the universal matter architecture. I have demonstrated that it should hold valid for both the macroscopic world in the gravitational domain, also in the atomistic world with regards to the bound muon decay rate retardation. Now, these are fine, but when I wrote the previous equation of motion, because it included the rest mass decrease, which will bring L-onuma size stretching and period of time stretching as well. So these are fine. But as far as the motion is concerned, we have not yet introduced quantum mechanics. We may not introduce the quantum mechanics if the particle doesn't behave wave-like in the gravitational world. But the particle may or may not behave wave-like, meaning quantally or quantum mechanical wise in a gravitational world. So I'm going to talk about these interesting quests now, and we have written very many papers on this. The previous energy conservation equation I wrote as the second equation. I am going to come to the first equation pretty soon. Now the second equation over here, as you see, the third equation, I'm sorry, it is the energy conservation equation, but we can write, instead of gamma times m sub 0 c square, which is the overall energy of the moving particle, HF. For a photon, this is anyway straightforward. But De Broglie in 1924, as we all know, all scientists know, wrote the first equation of this page, HF. He wrote this for a particle at rest to start with. But, borrowing this idea from him, we can write the same equation for a particle in motion. So if m is equal to m sub 0 times the Lorentz coefficient, then HF is equal to mc squared becomes the De Broglie relationship, the original De Broglie relationship. It is not the wavelength relationship of De Broglie, but this is the relationship which led De Broglie to his wavelength relationship. Lambda is equal to Planck constant divided by the momentum. So HF is equal to mc squared is the very first step of quantum mechanics, because it leads to De Broglie's wavelength relationship as to lambda is equal to the Planck constant divided by the momentum. HF is equal to mc squared is the main pillar of quantum mechanics. So we use this main pillar of quantum mechanics in our equation of motion, in its integral form. Of course, we can write it for the photon or for any other object. It's straightforward for the photon. And De Broglie says that it can be written for any object. We write for any object, and we come with the third equation of this page. And the differentiation of it furnishes a very interesting, simple ratio. Delta F divided by F is equal to delta alpha. It means that if a photon, but interacting quantally with the gravitational field, is set to a free fall, and its altitude varies a as much as delta alpha points to, then delta f divided by f, meaning increasing its frequency, relatively speaking, should be equal to delta alpha. This is checked out in the Pound and Repka experiment, which is achieved in 1959, but the experiment is not done for this purpose, really. But it checks this result for the photon. It means that the photon Pound and Repka used to prove the general theory of relativity correct behaves, as a matter of fact, quantally with respect to Earth's gravity, or the gravitational field created by Earth. So then, if the Broglie relationship remains valid, then the test object should behave wave-like. If not, if the Broglie relationship, meaning if HF for the gravitational interaction of concern cannot be set equal to mc square, it means that the object does not behave quantally or does not behave wave-like in the gravitational field of concern. It may behave quantally in a different gravitational field. For instance, the photons of concern, the Pound and Repka photons, they behave quantally in Earth's gravitation. But we know that I'm going to come to it pretty soon. Now we know that high energy gammas do not bend in the gravity of Earth. So it means that those photons do not behave quantally in the gravitational field of Earth. Now at this stage, we have introduced fully, I would say, the quantum mechanical inputs to our quantal theory of gravity. If we have this relationship, then the object shall behave quantally. Or if the object behaves quantally, we have this relationship. If the object does not behave quantally, then this relationship does not hold in the gravitational field of concern. It doesn't mean that this relationship would not hold valid for a different gravitational field of different intensity. Okay. Now, inserting the previous relationship, HF is equal to mc squared, m being the overall relativistic mass, to our equation of motion I had presented a few pages ago, then we land at this equation of motion with regards to the acceleration of the test object around a host body. The same idea can be, of course, applied to an electron moving around a nucleus, which does not exclude the quantum mechanical results brought up, but which also says that the object we described wave-like can indeed bear all alone its own particular quantal description as well. So this is of course not the equation of motion produced or led to by the general theory of relativity, which surprised many of our reviewers. Anyway, we are grateful to most of them, I would say, for having understood and for having accepted the novelty we brought over here. This relationship leads to all of the measurable end results of the general theory of relativity, which made the general theory of relativity so famous throughout the last century. For instance, we can right away see that if we have v, the velocity of the test object, getting near to the velocity of light, we have factor of 2 coming over there, and for a light grazing the sun, for instance, one can show that the final term on the right hand side drops off. I mean, its effect drops off of the equation. Then we have a factor of 2 coming in front of the Newtonian gravitational force. The last term, of course, brings along the 3 units of precession of the mercurial, for instance, bodies around the sun, out of 3, without any fault. I have already spoken about the gravitational redshift. So we have done with the results obtained by the general theory of relativity, but only throughout quantum mechanics. It's ironical, of course, to see that we obtained the results produced by the general theory of relativity in our quantum case. And the general theory of relativity is known to be utterly incompatible with quantum mechanics. So this is discussed in our paper published about a year and a half ago in Annals of Physics, and we wish you to check it, those who are interested in our theory, of course. And we have discussed how come the general theory of relativity and we can attain the same results, although we attain the same results general theory of relativity attains in our quantum case. We discuss how both theories can yield the same results. This is, I would say, devilish. In French, we would say diabolique. Diabolique in English as well. This is just devilish. Because the general theory of relativity fails, I'm going to say it pretty soon, in different cases, but the general theory of relativity holds valid in our quantum case. This is what is devilish. So, as I said, the foregoing equation of motion, which we based on the law of energy conservation and the de Broglie's relationship, which is the main pillar of quantum mechanics, ensures the centennial results predicted by the general theory of relativity in its favor. Again, let me restate it. So the above equation brings about general theory of relativity's bending of light within the accuracy of the measurement, of course. Similarly, it yields the usual full 3 units of precession of a mercurial planet around the Sun out of 3. Gravitational redshift is ensured by the theory, as I stated already right after our universal matter architecture's theorem. It's a quantum mechanical theorem. So thus we come to the thrilling result as to space-time curvature is now replaced by rest mass decrease and rest mass dynamics as well, and quantum mechanics. So lengths and periods of time are altered in our theory as well, but we don't need a metric equation, we don't need any fancy mathematical tools other than our integral energy conservation equation set to a constant in a closed system and the differentiation of it yielding the equation of motion right away. So the space-time curvature over here of the general theory of relativity is replaced by rest mass decrease. In general theory of relativity, mass increases in the field. This is another pitfall of the general theory of relativity, I would say, with great respect to the grandmaster. We all have been his students one way or the other, of course. I was only in the primary school when he died, but I was brought up with his legacy, I would say. So we don't have any contradictions, no fallacies, no energy conservation problem, whatever, and no incompatibilities with quantum mechanics. So we don't have space-time curvature as induced by the general theory of relativity, and other things that I'm going to speak of pretty soon. Now, this figure has got a long story behind. When I obtained, by the beginning of 2000s, my equation of motion, of gravity, applicable to the atomistic world at the same time, out of quantum mechanics, but I'm talking about now gravity again, I was asked particularly by Professor Ozan, my dear colleague, who we lost a couple of years ago. He was a great colleague and friend from Lebedev Institute. He was working on laser fusion, and he was very much interested in what I was doing. And we have written a couple of papers, perhaps a little bit more than this, with him. He was asking me, hey, Tolga, you have over here practically the same results, but how come you don't use the principle of equivalence of Einstein? You know, the equivalence between acceleration and gravity. I said, by the time I didn't know as much as I know now. No one of us knew by the time as much as we know now. I was joking. I said, come on, Slava. His name was Vladislav. I was calling him Slava. I was joking and saying, come on, Slava. I mean, I don't need it. Don't you see? I don't need any equivalence principle. An equivalence principle is an analogy. I mean, an analogy is always dangerous. If not set correctly, is not established the way it should. If you have any analogy, really, then it may mislead you. But of course, his question made me think a lot. Professor Marchal, on the other hand, our dear colleague, and he's living in Paris. He was the general director of research of French NASA, meaning ONERA, Organisation Nationale d'Études et de Recherche de la France. He said to me, Professor Yarman, you must find an experiment which should somehow display the differences between the general theory of relativity and your theory. I mean, you shouldn't leave it the way it is. Then, we started to think about it together with Professor Marchal, and this was about, by the time, 1999. So my energy conservation equations, together with its differential form and the equation of motion, was already there in 1999. Then I said, Professor Marchal, we exhausted everything in the solar system. What can we do next? I really don't see. He said, don't be discouraged and please think about it. It's very important, he said. He was the first Occidental, I must say, who backed up us and who supported very much our approach. He invited me to ONERA. I delivered a speech, a talk over there. We invited him over here to Istanbul. He came enthusiastically to back us up. Then I had the idea to realize the Gedanken experiment of Einstein. So the Gedanken experiment of Einstein is this. He takes a rotating object Okay, and then he looks everything from the exterior, from the outside, and then he considers that the effect of the rotating object should be due only to its tangential motion, which can be considered, he assumes, as a uniform translational motion, and the effect of acceleration as such, otherwise, it can be overlooked, if not negligible. You know, I have never left his book, The Meaning of Relativity. His last edition was made in 1956, and I was, by the end of 1960s, in 1968 precisely, I was at MIT, and I bought his book, The Meaning of Relativity. I started reading it, but I had difficulties to understand. Not technically, I would say, but I had difficulties to understand the physics. I mean, to affiliate with the physics he was developing, I must say. We have no problem with the special theory of relativity whatsoever, although this is another point to be discussed aside. But throughout the entire Quantal Theory of Gravity, indeed, we have used the special theory of relativity. We based ourselves on the special theory of relativity. We have whatsoever no problem with the special theory of relativity, I must say. Although this can be indeed discussed aside. But with the general theory of relativity, so it is based, as I said, on the clock hypothesis, establishing the equivalence of the acceleration, the rotational acceleration, and gravity, which sounds monumental if you are inside. You wouldn't make any difference between gravity or the motion. You know, if you have no signal from the outside, you would very well think that it is the gravitational pull which makes you pull toward the wall of the rotating object. This is a great insight, I would say. But to neglect the effect of acceleration as such, and assuming that the rotating object, you know, undergoes only the effect of uniform translational motion throughout its tangential direction alone, bothered me very much. All along, it bothered me very much. I was joking with Professor Rozanov. He told me, how come, Tolga, you don't need the principle of equivalence of Einstein? You know, besides that, I was saying to him that I don't need it. I finally invented the following joke. I said, Vala was the name of his wife. I sent them to their memories. I cannot join Vala, really. I called many times, but I couldn't join her. I couldn't join either Professor Rozanov's colleagues in the Lebedev Institute. Perhaps they are all retired. They must be all retired by now. So I send them all our love, indeed. I told him this joke. Look, Slava, you have 2 children, right? 2 of them from Vala, right? But do you need any other wife to have these children? And we laughed. And I said, well, you might have other children from other women, but from Vala, you know, you have only 2 children and you don't need any other woman for this, any other wife for this. So, again, this is to say that I was not by then aware how come the general theory of relativity, the clock hypothesis, its departure assumption might be checked or may be wrong. I thought about it, and finally I decided to make calculations on that, and I came out with the surprising result that the outcome of the experiment, Gedanken experiment, on which Einstein had established his clock hypothesis, should yield twice of what Einstein thought of. Then I presented my prediction to a conference held by Russian colleagues in Cairo. I'm passing this. Then I presented this in 2000. It was 2006. Then next year, I mean the year afterwards, I was invited to Moscow to make a presentation on our. By then we have written also a paper with Professor Arık and with Professor Rozanov, Slava and Metin. And I presented that prediction over there, showing that the clock hypothesis cannot be correct, the way Einstein thought. So my dear colleague, Professor Alexander Kholmetskii, was there as the chairman of the session. And the audience was very interested, and by luck, I would say, a speaker did not show himself. And Sasha, Professor Alexander Kholmetskii, asked me to continue to speak. And I extended my ideas in detail. And Russians, especially Professor Rozanov too, but more particularly Sasha, Professor Alexander Kholmetskii, was very much interested to redo indeed Einstein's Gedanken experiment. I mean, not redo, I mean, do realistically Einstein's rotating experiment. But I told him this. I told him, Sasha, I did this prediction indeed, but I checked the literature. I didn't find any results on that. So we rather check whether in the literature there are any experiments which would have been achieved on the subject or not. See? So I came to Istanbul from Moscow. He went back from Moscow to Minsk. He wrote to me a few days afterwards. He said, Professor Yarman, we nailed down an experiment. I'm sorry, the experiment is done in 1963, and the author Walter Kündig, this is his doctoral thesis, he just endorses with his experiment the results predicted by the generator of relativity. He said, he wrote, I didn't hesitate to write back immediately. I said, send to me this article, please, and check that article, please. If there isn't anything erroneous in this, I would be really surprised. So Sasha, a few days afterwards, wrote to me. So this all happens in 2007, and and then we come little by little to 2008. He wrote to me that, Professor Yarman, we have already pinned down an enormous error in data processing of Kündig. As a matter of fact, by that time, not only Kündig but other people, Champney and so forth, had done the experiment, and they all approved experimentally, the predictions made by the clock hypothesis established by Einstein's generator of relativity. So the clock hypothesis is the basis of the generator of relativity. So we decided to do this experiment, to realize this experiment. That was Einstein's Gedanken experiment. Sasha confessed to me that, before he sent to me this figure that I'm going to explain to you in a moment, he confessed that, Professor Yarman, when we started doing the experiment, we really thought that you would be falsified, your prediction would be falsified, and we were practically sure that we would come out with the same results as Kündig came out with. So what came out is this. So in the ordinate you have the count rate. So you have, first of all, a rotating system. It's called a rotor. You have a source, a radioactive source at the center of the rotor. You have an absorber at the end, and you have a counter outside. And in this experiment, though, the source and the absorber are co-rotating. Okay? So this is not exactly what I meant at the beginning, because I meant a source at rest. I mean, if we are to do this experiment with a radioactive source and an absorber at the edge of the rotor, but rotating with the system. So in my prediction, the source is at rest and the absorber is in rotation. In these experiments, though they are co-rotating, it's fine. So we needed to make some corrections, I should state. But this is the very first figure that Sasha had drawn in Minsk, either by the end of 2007 or by the beginning of 2008. So clearly, you see the data points, and you see in the red curve Einstein's prediction, based on his clock hypothesis. You see the clear difference. So Einstein's clock hypothesis cannot be true at all. It's not valid. It's not correct. It's incorrect. It's just a fallacy. Why it's a fallacy? We have made a lot of publications on that too. Let me say that, please, those of you who are fond of the generator of relativity, please don't take what I'm talking about personally. I'm not meaning to offend any of you. But here is the experimental results we obtained. We obtained the same results in 2014 in Istanbul. So if you don't trust them, of course, you have all the rights to redo the experiment, our experiments. But this experiment and the experiment we have achieved in Istanbul clearly put at stake, for the first time, very severely, I must say, the generator of relativity's basis, thus the generator of relativity. Of course, the question of how come the results of the generator of relativity, at least some of them, remain in perfect harmony with the measured results, this is a diabolic question, and I may come to it. Well, it's explained, as I said, in our paper published about a year and a half ago in Annals of Physics. Please check that out. No one had replied to that. No one had written anything on that article as of now. So this was what Professor Marchal was asking me, really. Professor Yarman, please think of an experiment where you can display the difference between the two theories. So we didn't have to go far. We did it in the laboratory. In the laboratory, the generator of relativity fails. It fails on the rotating clock experiment because the clock hypothesis fails. I'm sorry, but that's the way it is. I know how hurting it may be to see that something you believe throughout an entire lifetime may come out to be invalid. I understand this. but we are all scientists. If I came to be erroneous, which is very, very possible, I may come to be erroneous from now on. My colleagues and I may be in error. We might have mistaken. But you know what I would have said in that case? It was a nice exercise, and we now know that what we should eliminate and what we should keep. This is what I would say. So I understand how hard it is to see that something you believe throughout an entire lifetime, something to which you are imposed, you were taught, you learned excitingly, enthusiastically. Of course, it hurts you. It hurts people to see that it is incorrect. But the news is, of course, we had to fight against this because people either try to falsify our results or try to adopt it to the peculiarities of the general theory of relativity. And each time we had to work to show them to the scientific community and in prestigious journals, really, that they are in effect absurd. So this is what Professor Marchal asked me. The clock hypothesis doesn't work, and we are going to continue to see how things get along. Okay, so this was a page of the book of Einstein, The Meaning of Relativity. And I always found difficult to understand what he meant. Of course, I was reading and I understood what he meant, but I had difficulty to get affiliated with what he was advancing. So he has over here a footnote, and he says, these considerations assume that the behavior of rods and clocks depends only upon velocities and not upon accelerations. Or at least the influence of the acceleration does not contradict that of velocity, meaning the effect of acceleration, if there is an effect of acceleration. He says first that there is no effect of any acceleration as such. The only effect is the effect of the tangential motion, which is an idealized motion based on the tangential motion of the rotating object. But over here he says it doesn't exist, but if it existed, it can be overlooked. That I found incredible. Now, I was already a student at MIT, graduate student. I was about choosing my PhD thesis topic, and Professor Rasmussen, who was my supervisor and who knew that I was very successful, let me point that to throughout the doctorate qualifying exam. So once you are at that level, then you can choose any topic from any department. And Professor Rasmussen, who knew my feelings about general theory of relativity, said to me, wouldn't you like to choose perhaps a physics topic for your thesis? I was fascinated by nuclear reactor dynamics, and I said, no, I'm going to deal with this aside, but let me do my PhD thesis on nuclear reactor dynamics, and which I did with great enthusiasm also. But I did not forget about these sentences of Einstein throughout at all. So let's proceed. Now, some of you may not like to see this. These are astronauts or even ordinary subjects put into acceleration. Now, acceleration and change of acceleration, of course, are not the same thing. And you cannot attain any acceleration without any change in acceleration, any level of acceleration. So, as you see from these pictures taken in laboratories, either ordinary subjects, or these are anonymous pictures I chose for the presentation of concern in honor of dear Peter Rowlands. I made through Zoom in Crete to the international community assembled in Crete, Greece, I mean. So when you see these pictures, no one can affirm that these people are sailing on a pleasant cruise on the Mediterranean Sea on a summer day, sunny summer day, like they were in a uniform translational motion. They suffer. You may not suffer out of acceleration. We are all in an acceleration field right now. We are in the acceleration field of the sun. We are in the acceleration field of Earth. We are in the field of acceleration of the center of galaxy, and so forth. And we don't suffer really. And Einstein's insight may seem to many of us fine. If you are elevated with an elevator brought to an acceleration, then you may not differentiate between the effect of gravity, whether you are pulled toward the floor of the elevator or the fact that you are being pushed upward by the elevator. But there, and in the first example, I sit over here, I don't seem to suffer of anything. I don't suffer. I laugh. But these people, they are also in acceleration and they suffer. They are clearly suffering. No joke. They are not on a safe, pleasant cruise in a uniform translational motion. Why I don't suffer and why do they suffer? Because they are in a changing acceleration intensity. The acceleration I am sitting in right now is kind of a stationary, or I would say static even. Stationary because Earth rotates. Static kind of, and stationary as well, kind of acceleration. I don't see them suffering, but they do suffer. There is no way to bring the rotating rotor to a stationary acceleration without changing the intensity of the acceleration. So there is no way of bringing these people into a stationary acceleration without any damage. There is no way of bringing the rotating clock to a stationary acceleration without bringing to it any damage. It's called distraction. You can call it distraction. So the change in the acceleration is distracting. The distraction can be neglected. There are cases. For instance, we do speed up when we get closer to the sun, and the intensity of the acceleration, of course, changes. And we are not too much disturbed. We don't suffer that much, at least. These people do suffer because the acceleration changes just a little. The rotational speed of Earth around the sun is about 30 kilometers per second. It decreases about 1 or 1.5 kilometers per second as we get closer to the sun, and it decreases about 1.5 kilometers as we get away from the sun. So this is fine. We do seem not to suffer sensibly, I would say, but these people suffer. And didn't Einstein think of it? My dear colleagues ask me. No, he didn't think of it. As much as I can say, he thought of a stationary acceleration, which is fine. But there is no way to bring something to a stationary acceleration before you go through changes in the intensities of the accelerations. And nobody in the skies do exhibit a rigorous stationary acceleration. There is a rest mass dynamics. That's the point I wanted to come to. As my dear son Professor Ozan Yarman called it, he coined this term, rest mass dynamics. So they are, according to our theory, their body masses get decreased. How is it decreased? We made experiments on that. We made experiments with dental drills, and we made publications on that. We made a publication in 2013 in the prestigious journal, European Physical Journal Plus. We called it radiation from the rotating neutral bodies. As you bring a test object to a rotation, it must emit electromagnetic radiation. Its rest mass must get decreased. Now, what is interesting is that, throughout all these years, people tried to refute us. And I'm sure that our experiments, let me say a little bit more scientifically, I'm inclined to be sure that our experiments are done by other people. Because we are undermining the general theory of relativity, and this disturbs many people. We know that. We don't do it because we like to disturb people, no. But we are just any other scientist trying to pin down the scientific truth in between quotes. So if the clock hypothesis is as disturbing as these pictures are, and our experimental results are as disturbing as we see they are, throughout all these years, so it makes 16 years from 2008 to today, our experiments must have been redone. And what are their results? I like to ask this question to the scientific world. If you didn't do it yet, well, I would say it's not pleasant. It's a shame of you. But if you didn't do it anyway, please do it. Why do you wait to do our experiments? And this is the Gedanken experiment of Einstein. He says that, they should sail on a pleasant uniform translational motion. They do not. They do suffer. It's called jerk. The change in acceleration is called jerk. It's not a stationary acceleration. I am in a stationary acceleration, so to say, and I appear not to suffer at all. And there is no motion in the skies with any change of acceleration. Thus, the clock hypothesis must be wrong. I'm sorry. If you don't believe, please do the experiment. You spend billions of dollars. We respect that. If I didn't know, if I wasn't raised with Einstein's legacy, who I admire him already for his special theory of relativity. It inspired me a lot. I admire it, of course. But too bad, the general theory of relativity is based on an erroneous, and a fallacious, I would say, assumption. Okay, now we had to ask ourselves this question: how come does the general theory of relativity furnish results overlapping with our wave-like quantum case. This is also explained in the paper I cited, in our paper published in Annals of Physics about a year and a half ago. So, if a quantal object, meaning if an object behaving wave-like, it behaves quantally, meaning that we can write for this object Louis de Broglie's foundational equation, HF is equal to mc square. And the equation of motion I presented a few slides ago before this was based on that equation. So, that equation brings up a very interesting rest mass dynamics. Let's go. The theorem that we establish on that, based again on our UMA, universal matter architecture, is the following. Seeing as the mass at infinity of the test object decreases by an amount of exponential minus alpha being g times m divided by rc square, according to our energy conservation equation. Okay, so that was our energy conservation equation. The rest mass must get decreased. And this is due to special theory of relativity, and the special theory of relativity, when it writes delta m is equal to delta mc square, does not make any difference between, any distinction between the force which comes into the derivation. So it's too bad that the derivation is assumed to be valid for the nuclear world, but it's forgotten totally for the gravitational world, also for the atomistic world even. So seeing that the rest mass of the test object, the proper mass we can call it, at infinity is decreased by the factor exponential minus alpha, which we plugged in our energy conservation equation, which we set to a constant in a closed system, in a closed orbit, which doesn't bear any other objects around, okay? So then, because of the constancy of the energy conservation equation we have written, likewise, the denominator of it must also get decreased as much. This is induced by the constancy of the law of energy conservation written in a closed system by myself some 25 years ago. Okay, now thus, in the quantal case, and following de Broglie, the relativistic energy, HF is equal to mic square, which is equal to m sub 0 times c square times gamma, should increase as much to become m is equal to m sub I, which is the initial value of the object if it were cruising in empty space, by the coefficient exponential alpha. By the same token, the quantal frequency, f sub I, increases as much to become f sub I, which is the initial frequency, de Broglie's frequency of the object sailing in empty space, for which we had written m f sub I times h is equal to m sub I times c square, which makes that the corresponding quantal wavelength shortens as much. So we have over here, I would say devilishly indeed, the transformations Einstein pinned down with his clock hypothesis with regards to its rotating object, Gedanke rotating object, because according to him, the object's mass should increase, especially relativistically. Its size should get shortened due to the Lorentz contraction, and its period of time should decrease as much. But now, what Einstein, of course, could not visualize based on his clock hypothesis is this: we can write this theorem only in the case where, in our wave-like case, of course, only where the rest mass, which we call the core of the object, is decreased by exponential minus alpha. So this is a little bit tricky. I invite you to check if you are more interested. Our article written on this, and it did not receive any reply yet. People, as much as we gather, choose to keep silence. So very many of them, while trying to refute our experimental results and our prediction on that, saw themselves to turn down. We have indeed shown that they claim against our predictions, and the results were absurd. So far, it took about a year and a half. There is no reaction to our article published in Annals of Physics in 19th of May 2023. So this is what we call rest mass dynamics. In motion, the mass, as de Broglie conjectured, that was what triggered him, what intrigued him for a long time. So this mass increases, the frequency of it increases. This is called, de Broglie called it phénomène périodique. I called it the internal clock motions frequency. And that frequency turned out to be measured recently throughout many experiments. So I'm not talking about we are not theoretizing anything aside really than what de Broglie did and which turned out to be the foundational base of quantum mechanics, we use it. And I just state that frequency HF is equal to mc square. That's called the Breuss-Clock internal frequency. So it is not the special relativistically dilated frequency. Now, there is a factor of 1 minus v square over c square in between these two. So there is the Breuss increased frequency, increased clock frequency, which comes into play throughout the rest mass dynamics, both in the gravitational world and the atomistic world. That should hold the same way, without disturbing the already acknowledged quantum mechanical results that we are all raised throughout. But besides that, we have the right to talk about the test object, about its motion, and we have the right to talk about its motion quantum mechanically throughout the Breuss foundation equation. So the transformations I just stated over here in this theorem are theorem for a test object in a free fall, I said in the title, but we can call it the rest mass dynamics theorem. This can be called the rest mass dynamics theorem. We made an article on that for the Crete conference, and it's going to be published if it's not published yet. The article is ready, it's ready to be printed. We have gone through the proof. So you can read that, or you can check our academia corners to find either this presentation or the articles of concern. So you can check all these articles there as well, or you can check my academia corner as well. So devilishly, Einstein's kernel assumption as to rest mass increases because of rotation and size contracted, a period of time next to these two transformations is stretched, indeed match with the clock hypothesis assumptions, which gave rise finally all the way through to the Schwarzschild metric, because we know that lengths contract and periods of time stretch. So we don't need all that, of course. We don't need any curvature. We don't need any Schwarzschild metric. We don't need any metric to start with. We just have shown that the equation of motion we came out with fits very well corresponding Schwarzschild metric, which we don't need, as I say, again, because we didn't obtain it from that angle at all. But there is such a shocking, surprising match in between the two theories, but only in our quantal case. Let's continue. Now, this is an unlucky figure we have drawn and we have published in 2017 in Canadian Journal of Physics. Our editors were very brave. We must applaud them. You see our drawing of LIGO's gravitational wave signal over here. We have caught it exactly, I would say, but without having to base ourselves on gravitational waves at all. Our theory is totally different. The interaction doesn't occur throughout gravitational waves, but the interaction occurs between gravitational bodies in the skies through gravitational interaction, ordinarily with a speed which is about the speed of light. So anything which is caught by the LIGO and Virgo detectors or installations, we can reproduce them exactly throughout our quantum theory of gravity. Now, the sad part of this is that our editors, I must say obviously, I would say we can see it very clearly. They are put into a big oppression by powerful groups. We understand them, of course we don't agree with them. If they have anything against us, against our theory, they should write. I invite them to write again. As compared to these installations, we didn't spend a penny, I would say, in order to achieve our own experiments. It is just within $10,000, something like that. They spend billions of dollars. So it's nothing for them, it's peanut for them to redo our experiment. Please redo them if you did not do them yet. The fact that if you didn't do them yet, this is a negative point, I would say, from your point of view. But still, do it, please. And please do falsify us. And please do not oppress our editors. I know that they have demanded our editors to retract all of our published papers. This is not scientific. This is cruel. This is not human. This is far being sage. We are not doing politics. We are dealing with science over here. If what we are doing is erroneous, then you don't need billions of dollars to show it. You don't have to oppress our editors. Do our experiments and show it. It's so simple. Nothing difficult about it. But I am sure that you did our experiments and you came out with the same results and you cannot publish them. Then stop oppressing our editors. Okay, let's go a little bit further. As to dark energy, we published a paper on this in 2013 and it attracted little less attention than I thought it would have. What we did was to consider the entire known universe, compress it according to YARK Quantal Theory of Gravity. I mean Yarman-Arık-Kholmetskii theory, meaning that if you take this book and leave it to a free fall, for instance, then it would gain energy, but its less mass would get decreased, okay? So we do this toward the entire universe, the known entire universe. The number of protons is even known. So we compressed it with the energy the entire cosmos possessed. The kinetic energy is there. So of course, seeds of, I would say, electric charges inside a world, which we call cosmic egg. And this cosmic egg did not get any shorter radius than 2 billion light years. So this is fascinating because, I don't understand people to compress the entire universe to a point-like universe, which existed before the Big Bang. So we have no Big Bang. We have no bang, and it's not even big. We have just a cosmic egg and no mass inside, just kinetic energy, but just seeds of electric charges and so forth. So when we leave it to an expansion, then it starts with a zero velocity, but a given acceleration. This acceleration, we have calculated it. It's not difficult to calculate it. It turned out to be about 4.5 10 to the minus 9 meters per second square. So it's about Earth's acceleration, g, divided by a billion. About this, the order of magnitude. So this little acceleration at the beginning of the shifting of the cosmic egg, it started with a zero velocity with a given g, which I just stated. And that g, as the kinetic energy inside of the cosmic egg, of the seeds of matter started expanding, that kinetic energy started getting condensed as mass onto the seeds, and the acceleration gets decreased. So, if I throw this up, according to our theory, its less mass will get increased, but the kinetic energy will get decreased. So it's just the same idea, if you like. The kinetic energy is getting transformed in this conception into rest mass, gravitational rest mass. And what is important over here is that we recover Hubble's law, we recover many other things, which is measured, and we can compute how the acceleration behaves throughout. The acceleration gets decreased very quickly, and by now that acceleration might be around 10 to the minus 11 meters per second square. So it is the remnant of the initial acceleration, what is measured as dark energy. So there is no universe, according to this model, outside of our universe. There's an acceleration which is getting decreased and decreased as the particles fly away from each other. And there is, of course, still an acceleration which tends to zero. The parts of the cosmic egg which are at the outer side already attained the velocity of light. There are ceilings of velocities of parts of the cosmic egg staying in inner levels of it. So that acceleration decreases. But, we have neglected something very important over here, just to make things easier, naturally. We have not included a rotation. Meaning, according to the Heisenberg uncertainty principle, the cosmic egg cannot start getting expanded in a uniform transformational fashion. It must have some non-uniformities. Anyway, only these uniformities can bring up the galaxies. Some computation that I remember done some 40, 50 years ago. By the time I was at MIT, they were done by Crete computers in Princeton. Many particles were left to spread out, and only when a uniformity was included, they started to form things like galaxies. So things like galaxies getting formed means that there is no uniformity initially. There is no uniformity initially means that there must be something rotational through the expansion. If there is something rotational which no one takes into account so far, as much as I know, then the whole thing must start rotating around itself. And if we have this, then our gravitational theory, Quantal Theory of Gravity, says that there is no force for free, and you have to pay for the force. You have to spend energy to produce force, just to lift off a rocket. You have to spend energy in order to produce force to lift a rocket. So then, if there's rotation and the force which governs the rotation will not be for free, then there must be recollapse or collapse. Just like Hall-Taylor binary. We have a theory on that too. I'm not going to talk about that, not to prolong it much further, this presentation. So we also recovered dark energy. Okay, let's go to our slide. Now, the quantum mechanical interaction I talked about enthusiastically a few minutes ago is also very appealing. An interaction, as we all know, can occur with energy exchange. But according to this theory, it can occur without any energy exchange as well. Now, if it occurs with energy exchange, it cannot occur with a speed exceeding the speed of light. But in the case of lack of energy exchange, it can take place with a superluminal speed, as I have shown in our momentum conservation equation, which happens to be true in all bound ordinary electric or gravitational scenarios, which we call quantum mechanical interaction. So according to this theory, we don't see any gravitons anywhere around. We don't see any virtual photons. We don't need them. But interaction without any energy exchange can as well mean entanglement. I cannot go into that detail. We wrote an article about it. We're about to send it to be published. We hope that we will have understanding editors, open-minded editors, and we already have open-minded editors besides the people oppressing our editors. This is fine. We are accustomed to it. But this, of course, changes the entire outlook. So the sun and the planets are somewhat entangled, according to this view. They are quantum mechanically entangled. Because they have to pay for the force, of course, throughout billions of years. We can conjecture the planets will get closer and closer to the sun, but of course the sun's life would not last to see that. We can all see this anyway. So what I try to come to is that the entanglement or the binding of the planetary system or anything, the atoms are formed in the same way. They don't need any exchange particles. That's the idea behind. We have no exchange particles. We haven't based ourselves on any exchange particles to build the theory. To the contrary, we came up with an interaction exceeding the speed of light. And this is beautiful. And you know what? This resolves the long-lasting paradox between quantum mechanics and the special theory of relativity. You cannot exceed the speed of light if you have an interaction throughout an exchange of energy. But the interaction can occur quantally, thus without any energy exchange, and with a speed which is ordinarily greater than the speed of light, as Ozan calls my son, Professor Ozan Yarman, superluminality permitting velocity. So we have no problem with the special theory of relativity. Let me repeat it. We have no problem with quantum mechanics. We have recalibrated quantum mechanics because even in Dirac equation, you don't have FDR is equal DMC squared. So Dirac, whom I have the honor to have met with, he did not consider the electron's rest mass decrease when the electron is bound to the nucleus. But the bound muon shows that the rest mass should decrease according to our Umat theorem. The quantum mechanical theorem, which I have shown some 25 years ago, even before than this, some 30 years ago, the Umat theorem, together with the law of energy conservation, makes that the bound electrons' rest mass must get decreased. Where we don't need any virtual photons, we don't need any gravitons. The same occurs based on special theory of relativity for the gravitational world. And very unfortunately, I don't understand how that could occur. The derivation of the relationship delta M times c squared is equal to delta E, meaning that the energy produced should be paid by the rest mass deficit. The derivation of this basic outcome of special theory of relativity does not make any distinction between forces. It is valid for any force. Thus, it should be valid for electric forces. It should be valid for gravitational forces as well. I'm glad that we have included finally the force, which is nothing than pull or push. Force is force. It's push or pull. I'm glad to have recovered this concept because in the general theory of relativity there is no push, no pull. It's beautiful though. Mass tells the space how to curve, and the curved space tells mass how to move. This is beautiful. This is very poetic. But things does not occur that way. If you forget about the force, you lose energy. Force works, energy is produced. So the concepts we base ourselves on are very simple, and we somewhat recalibrated, as I said, quantum mechanics in order to remove the discrepancies between measurements and theoretical predictions. We have published on that. We unfortunately had to remove totally the general theory of relativity. We have solved the information paradox. We don't have any information paradox. We don't have any singularities in our approach. And I forgot to tell you, the general theory of relativity does not work in our particle-like case. In our particle-like case, where we cannot write mc squared is equal to hf, the de Broglie's foundational relationship, then light's photons do not bend. Very high energy gammas do not, for instance, bend on Earth gravity. They may bend elsewhere, But they don't behave wave-like on Earth's gravity, when embedded in Earth's gravity, on the Earth's surface. Anything can behave wave-like or particle-like, depending on the interaction conditions. So Einstein's general theory of relativity is unable to predict this. It fails over there. It also fails on its basis. The rotor experiment that we have realized, that is originally Einstein's Gedanken experiment, clearly showed that general theory of relativity fails on its basis. Sorry. If anybody, if any institution loves to contradict us, to falsify us, all they have to do is to redo our experiments. That's it. This is not enough. They have to explain how high energy gamma photons do not bend in Earth's gravity. It's Garibian's experiment. It's all written in the reference list Ozan Yarman provided. So we have one more slide, I think. This was Ozan Yarman's surprise. Ozan Yarman has prepared these slides. Let me point this. And he is also monitoring the entire presentation right now. So, let me conclude. Both Coulomb force and the Newtonian force hold, though just for charges and masses strictly at rest. Now, those of you who are familiar with Coulomb force are taught that the Coulomb force is valid for when the source charge is at rest, but the test charge is at rest or in motion. It's not true. I mean, according to this approach, it holds only when the electric charges are at rest with regards to each other. And the Newtonian force holds with masses at rest with regards to each other. We didn't borrow the Newton force from the Principia, Newton's work. We have shown that the 1 over r squared dependency of both Coulomb force and Newton force is a requirement of the special theory of relativity. We have also shown that the capital G gravitational parameter that enters the force expression is only a universal constant in the local observer. I mean, all observers, just like Cavendish did, will measure the same gravitational constant but in their own laboratory, locally. The distant observer would assess differently that gravitational parameter. But this, I find, a detail within the framework of this presentation. So, the Coulomb force, we don't alter it, except that we consider this force with regards to electric charges only at rest with regards to each other. Newton force, we touch it a little bit. We touch it because the gravitational constant is different for the local observer and the distant observer. All local observers will measure the same gravitational constant. The rest mass gets decreased in gravitation as you go deeper and deeper, closer and closer to the center of the host body. So these are peculiarities that we have discovered and we had to input into our theory. Newton himself had doubted that when he wrote F is equal to ma. It's not a definition of force, it's just a description of force. And F cap sub G is equal to G times capital M times the rest mass of the test object divided by R squared. So he doubted whether the two masses of the test objects that enter into these two force expressions are the same or not. We discovered that they are not the same. So all this, I would say, and nothing more, I would add, ensures to unite the macro world and the atomistic domain. We are just the same mathematical tools or framework we have coined. And all this is simple. The mathematics we have provided do not go behind, let's say, university graduate levels, beyond that. I would say you don't need any fancy mathematics. Why? Because we did not need any of it. We didn't need any fancy mathematics. It's not that we are not familiar with fancy mathematics, but we didn't need any fancy mathematics. So all this can be conveyed to students much more easily than the general theory of relativity. And I didn't learn the general theory of relativity when I was doing my undergraduate work in France, but I started learning it chiefly at MIT when I was getting prepared for my qualifying exam. And then I started seeing the pitfalls. So then rest mass or the same rest energy decreases when bound to a force field. So this is a primordial premise of our approach. Rest mass or the same rest energy. We don't make a differentiation between rest mass and rest energy because rest mass is nothing else than rest energy, assuming that the speed of light is unity. So rest mass or the same rest energy decreases when bound to a force field. All rest masses should decrease when bound to an attractive force field. They get increased when they are repelled by a force field. Now, what is interesting over here is that our rest mass and rest energy do vary in the same direction. Whereas in the general theory of relativity, there is the schizophrenia. Mass increases because of the cloak hypothesis in the gravitational field and the energy is decreased. Our approach, while this is in full symbiosis with quantum mechanics, is much simpler and much more complete than the general theory of relativity. I'm really and terribly sorry for those of you who are very much fond of the general theory of relativity. I am very much fond of Einstein's work, but this is how science can get progress. I mean, we have no right to make any religion out of our scientific knowledge. If someone comes with proofs which falsify, experimental proofs which falsify our results, I'm ready to say that that was a nice exercise and we are ready to leave it. No one did it yet. It's applicable to all bound fields, either the atomistic field or to the gravitational field. So we have no boundary between atoms and gravitational world. So we remove the information paradox by deriving no singularities. Really. We have no singularity whatsoever. I mean, I have seen very respectable physicists, colleagues, who ask me, but you are trying to understand everything. I say, in science, what else can we do really if we do not try to understand everything? I mean, we cannot leave things over somewhere there not having understood any of it. So the way I see the general theory of relativity is somewhat transformed into a scientific religion. None of us has this right. I invite all of you to falsify us, but forget about, please, to transform the general theory of relativity into a scientific religion. Next, though we have no singularities, we have, of course, supermassive bodies where Doppler-shifted radiation will eventually leak out. So we have no Big Bang. It's not even bang, nor is it big. We have just a soft sifting off from an initial inferno, which we call a cosmic egg, of radius of about 2 billion light years. Then from there on, we have exactly the same prediction of the cosmological literature. The velocity of light gets increased to attain a ceiling, and we have the dark energy acceleration and so forth. So we have the Hubble's law and so forth. So we could explain dark energy. This presentation took a longer time than I thought it would. I thank all of you. We would love to hear of you, of course. Try to criticize us, but sagely. Don't get offended, please. And those of you who feel against our views, please do your experiments and come out with your results. Thank you to all. Bye-bye.